All right, good morning, everyone. Can you hear me at the back? It's all good? All right, so I've been charged to teach a lecture on hydrodynamics, and here's how the conversation went. Matteo, who's not here, so I can just say whatever I want. Hi, Pascale, would you like to give us a 1.5 lecture on hydrodynamics? And I said, I worry that covering all of hydrodynamics in 1.5 hours is impossible. Can I assume the students know fluid dynamics equations at least? And he said, no. I think the idea is to cover the basics, fluid equations, waves, and shocks. So that's... All right. So in my mind, I was like, but what about turbulence? What about instabilities? And nope, fluids, waves, and shocks. So here is the plan. The equations of fluid dynamics, and then I'll talk about compressible effects, sound waves, and shocks. And just for disclaimer, I don't actually work on anything compressible. All my research is about fluid dynamics in stellar and planetary interiors where we are almost incompressible. So I'm teaching something I have neither ever learned before nor taught before, so I'll do it very slowly. So let's start with the governing equations, and perhaps just a definition of what a fluid is, because maybe that's useful. From Wikipedia, which is actually not a bad source, fluid is a substance that continuously deforms under applied shear stress or external forces. And so for the purpose of this lecture, a fluid will be a gas or a liquid. And the only difference between gases and liquids is the equation of state. So things that I will ignore in my lecture, but that will be taken into account by lecturers after me, are things like multi-component fluids, so when you have phase changes, or MHD effects, or general relativistic effects, and also non-Newtonian effects. And non-Newtonian effects is nothing to do with general relativity. It's about the properties of the stress-strain tensor. So for example, if you argue that cats are fluids, which I'm not really sure about, they are certainly very non-Newtonian. So we'll also ignore cats in this lecture. So non-Newtonian, to be specific, are things like butter, toothpaste, shampoo, mud, volcano, lava, etc. Anyway, so looking at Newtonian fluids, liquids, or gases, the equations that describe their evolution are essentially the same across most of the universe, starting from fluids on our planet, water, atmosphere, fluids in giant planets, stars, accretion disks, star-forming regions, the entire universe. It's essentially the same basic equations with a few added effects and microphysics that differ between them. There are lots of different ways to get at the equations of fluid dynamics. And the very traditional one, the oldest one, is to look at it from a Newtonian perspective and to say each fluid element evolves according to the equations of motion derived by Newton, meaning that they will move according to applied forces and they will deform according to applied stresses. And so you will find lots of textbooks with that derivation of the equations of fluid dynamics, and that's the one I'll take today. And just for the one that we use in Santa Cruz is the Kundu textbook, but there are lots of other ones that you might want to use. A more modern approach towards the derivation of the equations of fluid dynamics started basically when we realized fluids and gases are made of smaller components, which are atoms and molecules and other things. So that modern approach looks at the fluid as a collection of these infinitesimally small particles. And the equations of fluid dynamics can be derived as moments of the Boltzmann equation, so in a statistical mechanical way. So here you think of lots of atoms or molecules that each have their individual velocities. And for example, the local velocity of the fluid will be an average of these. And the density will be an average number of particles times their mass divided by the volume kind of thing. And so this is the approach that you will find, statistical approach. And for example, the Frank Xu Physics of Astrophysics Gas Dynamics book has this approach in there. And then there's even other ways looking at variational principles for fluids, and you can rederive them that way. But I'm not even going to go there. So we're going to look at very simple mechanistic way. And the way to start is to look at mass conservation. That's usually how you start. So you think of a domain whose boundary is a domain D whose boundary is partial D. And the key for that particular derivation is that this domain is fixed in space and time. I'm not allowed to move it for now. And there's a fluid flow going through the domain, and that fluid flow is bringing in mass and taking out mass of the domain. And so the conservation of mass will start by saying that if I integrate the density in the domain, and if I want to know what its time derivative is, it's simply going to be whatever is being brought in by the fluid minus whatever is being brought out by the fluid. And you can conveniently write it as an integral over the boundary of the domain of the density times u dot n with a minus sign in front. And the reason it works is if the normal to the domain n, which is always taken outwards by convention, if that one projects on the velocity field in a positive way, so when n and u are pointing in the same direction, then the dot product will be positive, and so you expect mass to be taken out. And so you have to have a minus sign here. And similarly, if u dot n is negative, as it would be here, for example, u is this way, n is this way, that's bringing mass in. And again, negative, negative gives you a positive. And if u is parallel to the boundary, you're not bringing or taking anything out. And so in that case, that dots into 0, and it doesn't contribute to that integral. Now, earlier I mentioned that the domain must be fixed in time and space, and if you do that, you can actually interchange the order of the d by dt and in the integral sign to bring that d by dt inside. And then you can also, from here, use the divergence theorem to rewrite this u dot n dx times rho as divergence of u dot n, divergence of rho u, this time over the entire volume. So that's just straight application of the divergence theorem. And the final step is to say, this was true for any domain D. I didn't pick a very specific one. I randomly said, let's consider a domain D. And because that has to be true from any domain D, what has to be true is that the integrand must satisfy that relationship. And that ends up with d rho dt plus divergence of rho u must be equal to 0 at any point of time and space. So that's the mass conservation equation. And written in this form, it's called a conservation law. When you have a quantity, derivative of a quantity plus divergence of something which we call a flux equals 0, that's a conservation law. And we'll see many more examples of conservation laws. Yeah?
I think on the right-hand side, dimensionality of the integral.
Oh, yeah, sorry. d2x, d3x, apologies. All right, so that was the easy one. Now, one of the key aspects of mass conservation, for instance, is what we can make of it. So let's take that divergence of rho u and expand it using just basic vector algebra, differential vector calculus. So you get u dot grad rho plus rho d view, and I'm going to shove the rho d view on the right-hand side. And then these two quantities, I'm going to join them together to create a big D by dt. So big D by big dt is just partial with respect to time plus u dot grad. And that quantity, this d by dt, is called the Lagrangian derivative. And it's a derivative that follows a parcel of fluid as it moves. Now, it might not be obvious that this is the case, so I'll show you where that comes from. So to understand why this big D by dt is a derivative following the fluid, consider that each of these parcels, the red, blue, yellow, blue, and red parcels, at a given time t, came from a specific initial condition at time t equals 0. And this was the trajectory that the parcel made over the time from 0 to t. The interesting thing is that as long as your fluid is either completely incompressible or weakly compressible, the mapping between initial condition and final position is unique, meaning that you don't have two parcels actually colliding at a finite time t. You end up in the same position. So it's a unique mapping from initial to final conditions. And so that mapping can be viewed as the change of coordinate. So instead of referring to a parcel as being at position x, y, and z, I can say, sorry, as being at position x, y, and z at time t, I can say this is the parcel that came from x naught, y naught, and z naught, and propagated up to the new position at time t. Now, I know this distinction is a bit weird, but what the key is if you want to do a derivative following the fluid, the only thing you have to do is a derivative at fixed initial condition. Because if the initial conditions are fixed, it's still the same parcel that's moving, okay? So this is how to mathematically create this idea of following the fluid. So it's just a derivative as a function of time, but fixing the initial condition. And to do that, we have to actually express that mapping mathematically, and you can do it this way. So you know that the derivative of position with respect to time is the velocity. And so if you rewrite this, you can integrate it, and the position at time t is just the initial position plus the integral. And here, there's a little bit of trickery here, because it's, again, an integral following the path of the element. But it's the integral following the path of the element of the velocity it had as a function of t. So let's now put all of this together. So if I have a quantity, f, which in a normal description you'd write as a function of f of x, y, z, and t. Now I want to write it as f of x of t, y of t, z of t, and t, where these new variables are related to the initial conditions in that way. So then the total derivative of f as a function of time will have both a partial derivative due to that term, but also you're going to have to use the chain rule to get the derivatives with respect to x of t, y of t, and z of t. So that gives you a df dx, dx dt, df dy, dy dt, df dz, dz dt. And this dx dt is actually the velocity in the x direction. The dy dt is the velocity in the y direction, and the dz dt is the velocity in the z direction. Is that okay for everybody? And so at the end of the day, you get with the partial derivative of f with respect to time plus u dot grad f. And that is this total derivative following the fluid that I mentioned earlier. Okay? And I had just, if you've never seen this before, I had to see it a gazillion times before I really internalized the idea. It's either obvious or complicated, depending on who you are. And for me, it was tricky. But finally, I think I understand. I've been working on this for 20 years. It took me a while to really, really see, does that really work? And yes, it really works. So, so going back to mass conservation, I just wrote this, right? So this is now the same mass conservation equation written with its total derivative following the fluid. And you could see that now the total derivative of density following the fluid is just minus rho div u. And to understand this physically is quite easy. The first thing is that if div u equals 0, mass is conserved following the fluid. So d rho dt equals 0, mass is conserved following the fluid. This is the incompressible limit. So you can't push more density into the fluid if you actually don't push the fluid together, so if div u equals 0. So div u equals 0 means that there's no divergence or convergence of the velocity field at any point in the domain. Now what divergence and convergence would do, suppose you have convergence of the fluid, so this is div u smaller than 0, and you could see that this would imply a d rho dt that is positive if div u is negative. I'm assuming density is always positive here. On the other hand, if you have a divergence of the fluid, the div u is greater than 0, and so this d rho dt will be negative. So that sort of makes sense. If you push the fluid together, you're going to increase the density locally, and if you pull the fluid apart, you're going to decrease density locally. Okay? And again, following the fluid. So this is mass conservation. Maybe I'll write this on the board because we'll need it later. Okay, so next is momentum conservation. And here, this is where we're going to use Newton's law. So Newton's law is just applied to a solid body that can't be deformed is just F equals ma, or rather m times the acceleration du dt is the sum of the forces applied to your fluid, to your, solid body, if it's a solid body. So for a fluid element, it just becomes rho, which replaces mass, times du dt, the derivative following the fluid. And it makes sense that it should be the derivative following the fluid, because there's no point in expressing the acceleration somewhere your fluid element isn't. So you are always applying the acceleration, is always using the derivative following the fluid, because that's where you want your fluid element to be. And then you have the sum of applied forces. Now, this might be all the body forces applied to the fluid, which would be equivalent to this. So in there, you might want to put things like gravity, the Lorentz force. If you have particles, it would be the drag of the particles on the fluid, all sorts of stuff. On the other hand, these two are specific to the fluid equations. So there's a gradient of pressure with a minus sign, and then the so-called viscous stress tensor, which is an internal measure of stresses within the fluid. And I'll come back to that one in a minute. So maybe I'll do this. Is it working when I do the equations on the slide? Because normally I would do it on the board, but maybe it's better if I do it on the board? What do you prefer? Board is better? Board is... I just want to make sure everybody has time to... all right, let's do it on the board. So I mentioned earlier that we had the density equation in a conservative form, and now the momentum equation that I just showed you was not in a conservative form. So how do we put it in a form that's conservative? And the key is to start with what we have. So rho du dt, and then there's the bits on the other side, and I'm going to rewrite it as rho. I'm going to expand the Lagrangian derivative, or the derivative following the fluid. And then I want to write this here as a full derivative, d by dt of rho u. But now I've added a term which I need to subtract, so it'll be minus u d rho dt plus rho u dot grad u. And then in here, I'm going to then substitute the conservation equation for density, which was div rho u, d rho dt plus div rho u equals 0. So that term turns out to be plus, you have to change sign, div of rho u, and then everything else is the same. And then now this one conveniently combines with the next one. You could see that I have a u div of rho u, and then rho u dot grad u. And so that's going to be div of rho u u. And it's not a dot product, it's a tensor that's associated with both of these vectors. So that's how you get to this point. And that's what I wrote over there. And so now you replace the left-hand side of the momentum equation by this new form, and you have still on the right-hand side, you have all your forces. Now, the other thing is you can rewrite the gradient of P as the divergence of P times the identity matrix. And here's my stress tensor here. And then you have the sum of all the other forces. And among these other forces, there might be some that can be written as the divergence of a quantity, and some others that cannot. But just for the sake of simplicity, I'm going to leave them all outside. And so now you can see that you can combine all these divergence terms together into a single flux, which will be the momentum flux. So I have d rho dt of rho u plus the divergence of this momentum flux is going to be the sum of all the other forces. And in here, we could see three contributions. This one here is called the Reynolds stress, rho u, and this is now the symmetric part, which contains the pressure, and then you have the viscous stress tensor. Okay? And this viscous stress tensor, this is the bit where it can become extremely complicated if you have non-Newtonian fluids, so that have very complex reactions to stress. For very simple gases and liquids, which are composed of non-interacting particles, except for collisions. You have this very simple form, which is a number times dvu times the identity matrix, plus the symmetrized version of the stress, which is rho nu times grad u plus grad u transposed. And in Cartesian coordinates, for example, if you want, you can write it like this. So you have, again, the same term here with the delta ij corresponding to the identity matrix. And here, this is basically the derivative of uj with respect to xi plus the derivative of ui with respect to xj. Okay? And kappa and nu depend on these microscopic properties of the fluid. So this is something that really depends. So if I have a gas or a liquid, they're going to be different. Now, it very quickly becomes very complicated if you are working with interacting particles that have forces among them. It also becomes very complicated if you have a non-Newtonian fluid where you might have a finite, you might have a very nonlinear stress-strain relationship. Okay, here it's linear in the strain. And then conveniently, but none of you do incompressible fluids except me, it seems, for incompressible fluids, if dvu equals 0, this comes out completely. And if, in addition, rho nu is constant, then you take this out, and you end up with a very simple form that a lot of people usually remember, which is that the divergence of the stress tensor is proportional to the Laplacian of u. But that's really in these very specific conditions that are specific to incompressible fluids with constant rho nu. Okay. Any questions about this so far? All right. So now comes the next part, which is, let's count the number of equations we've got. We've got 2 equations, momentum and mass conservation, but we have 3 variables so far, at least, pressure, density, and velocity. So you need 1 more equation at least. And you can get one from the equation of state. And an equation of state, generally speaking, relates 3 thermodynamical quantities to one another in all generality. Right? So for example, you can write it as pressure as a function of density and temperature, or density as a function of internal energy and other things. So you can write many different versions of an equation of state. For a perfect gas, the pressure is the gas constant times rho T, where this is a gas specific. Or you can write it more universally as the universal gas constant rho T over the molecular weight. For a liquid, often, though not always, the density is just a simple function of temperature. Okay. For if you have a polytropic process, which is pretty commonly discussed in astrophysics, the pressure is going to be a function of density only, and often you have these power laws relating the two to one another. So the equation of state is really specific to the problem you are considering. But you can see that except from this particular example, which is particularly convenient, in all the other cases, you introduce yet another variable, which is temperature, or your other thermodynamic variable. So now we have 3 equations with 4 variables. And so you still need another equation. You're not quite done yet. Now, the last one can be obtained from energy conservation principles. And the way to usually start, there's again lots of different ways of arriving at an energy equation, is to use laws of thermodynamics. So here is one of them written in this context. So this is E is the internal energy per unit mass. And so this is saying that the change in the internal energy per unit mass following the fluid times the density is this term here, and that comes from PDV work. And you can show pretty easily, and let me do this here, that this is actually rho P div U. So remember that so that's so just to be specific, this is a bit like rho times PdV, as long as V is 1 over rho. Are you okay with that? So if V is one over rho, and I get, so that would be the specific volume per unit mass, then this is going to be d by dt of 1 over rho times rho. And then this is p over rho, d rho dt is minus rho d view. The rho's cancel out, so you get minus p div u. Okay? Sorry, did I do this right? Yeah, I guess so. So I might have an extra row somewhere. So this row should not be here, I guess. And then, so this is just the PDV work. And then for these terms, these are all non-adiabatic terms, and I'll explain that in a second. These are all terms that bring heat into the fluid or take it out of the fluid. So, for example, there's this, which is the local production of energy per unit mass, times mass, the local production of energy in the volume. So this could be, for example, from nuclear reactions. If you have Newtonian cooling, you can add Newtonian cooling, for example. If you're in a deep interior of a planet, you can have radiogenic heating. This one is the heat flux in and out of your volume. So if you're in a conductive environment, so this is just proportional to the gradient of temperature, but it could also be radiative heat flux. And the last term is the viscous heating of the fluid due to the viscous stresses. Okay, so all of these contributions are non-adiabatic, so they bring heat in and out of your element. So the change in internal energy is basically due to compression or expansion effects, and all these bits that are bringing heat in and out. And another way of deriving it would have been to say, I'm going to take the second law of thermodynamics, which is just dE is TdS plus PdV, minus PdV, plus PdV. And then you rewrite it as a change following the fluid, as you would do. And combining this, you could see that this is exactly the term we had on the other slide, so here and here. So what you're left with from the other slide is just a TdS bit. So here. And I think I got my signs wrong. This is why I'm confusing myself. This should have been a plus. No, this should have been a minus. Sorry, here we go. And so now this TdS, which is the specific entropy, changes of that specific entropy are only due to non-adiabatic effect, kind of obviously. And so you have, again, the heat flux, the local production and dissipation, and then the viscous heating. So if you ignore any non-adiabatic effect, so if you conserve heat along the parcel path, ds by dt is 0. And this is an equivalent equation that you can use if you know your process is adiabatic, so there's no change in the heat, okay? So you can use that instead of energy conservation if you know you're adiabatic. So there are different alternative ways of writing this heat equation, so either this or many other different ways, depending on which thermodynamical quantities you like to work with. And I will correct my signs before I put these online. Now, one of the things that's key, though, is that it's not internal energy that's conserved along a particle path. So if we want to create a conservation law, we have to look at what's really conserved, and that's the total energy. So including both internal energy and kinetic energy. So to see that, let's work from here. So this is, again, the equation I wrote earlier. And for simplicity, I just removed the heating and the heat flux, but you can add them if you want, right, in each equation. So let's just write this here. I'm so short, it's almost pointless. I mean, really, you can see it. Let's just work with that, it's fine. So this is the equation I wrote earlier. So we're going to play this trick again of taking everything that's on the right-hand side and making it, in as much as possible, writing it as the divergence of a flux. So for example, this P div u term, I'm going to rewrite it as div of pu. But because I did that, I need to, because it was a minus, I need to add u dot grad p. Okay? Now, grad p, you know from the momentum equation that rho du dt is minus grad p plus divergence of the stress. So you can solve for grad p and substitute it here. So this is what grad p is coming from the momentum equation. And then the really nice thing that happens is that u dot into du dt is basically d by dt of u squared over 2. So that's the standard equation. And then you take that and put this on the left-hand side. There was a rho, which is conveniently there, which you can factor out. And so on this left-hand side, you end up with rho d by dt of e plus u squared over 2. Okay? And then on the right-hand side, you're left with minus divergence of pu. And then you might say, well, what about u dot grad s and phi? Do you know what happens to these? This was viscous dissipation, the viscous heating, and that ends up being exactly minus the viscous heating term. So this and this cancels out, okay? And it's basically when you have viscous heating, it takes, this viscous term takes, in some sense, if you think of it energetically, it takes things out of the momentum equation, puts it into the heat equation. And so when you add the two, they cancel out. And so, so now we're here, but this is still not in conservative form. So this one I will do in the board. So you have this rho d by dt of e plus 1/2 u squared. And now I want to write it as rho d by dt of e plus 1/2 u squared over 2 plus rho u dot grad of e plus 1/2 u squared. Okay, and then I'm going to, actually, there's a quicker way of doing this, which is first to write that this is d by dt of rho e plus rho over 2 u squared minus e plus u squared over 2 d rho dt. Okay, so again, playing this trick of creating a total derivative and then subtracting whatever we just added. And this is now d by dt. So this is, we're going to call it the total energy. So it's dE by dt plus u dot grad E minus, now d rho dt, remember, was minus rho dvu. Okay, so now I have a plus. The rho times this is E. And I end up with a dvu. And now you end up with the e dt plus the divergence of EU as a conservative form, okay? And then, so that was for the left-hand side. And now on the right-hand side, there was a p dvu, there was a pu here. So when I combine everything together, I get the conservative form of that energy equation, which is the e dt plus div of E plus pu equals 0, where E is the sum of the internal energy plus the kinetic energy of the fluid, okay? So in summary, we have these equations that are governing the dynamics of a fluid. You can either write them in Lagrangian form, so things conserved along particle path, which are density, velocity, and internal energy, or you can write them in conservative form as the derivative of a quantity plus the divergence of a flux of that quantity. And in a lot of CFD codes, you will see the conservative form used, though not everywhere. But it's a very useful form to think about. And then, of course, on top of that, you're going to have an equation of state, which is going to relate to 3 of your thermodynamic variables together. Okay? Any questions so far about the fluid equations? So if you're so lucky as to have a process that's barotropic, where P is a function of rho only, or polytropic process, which is a specific barotropic one, then you don't need that extra equation of state. But typically, you're going to have a total of 4 equations. Now, like I said, the same 4 equations actually describe the evolution of all these astrophysical, and I consider that astrophysical to some extent, is the same equations for all of these systems. But of course, you have to add the extra physics. So these little dots that I kind of left out there, right? So when you do, for example, Earth atmosphere, ocean processes, you're going to have to add condensation, evaporation, and radiative transfer for the energy. In here, similarly, you're going to also have to add magnetic fields. In the sun, you're going to have to add nuclear generation into your heating equation. In accretion disks, you're going to have to add dust and all the interaction with the dust. You're going to also have to add self-gravity if you do massive disks. In stars, star-forming regions, what's really going to be key is self-gravity, magnetic fields, radiative transfer, and dust. And then when you do global cosmological simulations, you have to also add general relativistic effects and dark matter. So all of this has been completely neglected so far. It's in the dots in these equations that we've been ignoring, okay? So the next step is to look a little bit about the dynamics of these equations. So, and the main one that I've been tasked to teach you about is compressibility. And compressibility is really key to some of these objects and is almost incidental or accessory in the others. And specifically, unless you're actually, doing aerodynamics and trying to design fighter jets or that kind of stuff, you're going to mostly ignore the effects of compressibility on Earth. And again, they're not particularly important in planets and the sun, except very high up in the atmosphere. The best you're going to have are sound waves, okay? On the other hand, compressibility effects are completely key to the dynamics of these other objects. So, and the main difference is in the density of the gas. So these are fairly dense fluids, and these are fairly tenuous, low-density environments. And so we'll see the types of compressibility effect that occur in here, which are sound waves, and the type of compressibility, or dominate, I should say, the types of compressibility effect that dominate in these objects, and the type of compressibility effects that dominate in these objects, which are shocks. So let's talk about sound waves. You can actually feel the sound waves when I'm talking. So in planets and stars, more specifically, everywhere else in the universe too, but specifically in planets and stars, you're going to be permeated by sound waves. And they're particularly important in what we make of them, which is helioseismology and astroseismology. I don't know how many people in the room actually practice these fields. I know this is not quite the right school. Okay, so helio and astroseismology use sound waves to infer properties of interior stars and planets. And so this is why they're important in astrophysics, but also for the purpose of this school, they are what I think is the very simplest form of fluid waves. And so if you understand how you arrive at the equations of sound waves, you can probably do almost all other problems in astrophysics. So to model them mathematically, and this is going to be really important, we're going to assume that the background, whatever fluid you're considering, is in a steady state. Or if you actually know about asymptotic theory and multiscale modeling, you can assume that the background is evolving on a time scale that is much, much longer than any wave time scale. Okay, that's also okay. But for simplicity, until you learn about multiscale modeling, we're going to assume the background is in a steady state. We're also going to assume it has a background density rho naught and a pressure P naught, both of which can depend on space, but again, are steady state. And there's no pre-existing motion to the fluid. There's no velocity field in the fluid that pre-exists. And we're going to ignore forces of gravity, we're going to ignore viscosity, anything other than pressure gradients in a momentum equation. Again, for simplicity. And there's a little star here that says, assumption should be checked a posteriori for each application considered. So it could very well be that you make this assumption, it's completely wrong. So you should always check after the fact that this was a correct assumption to make. And then you assume small perturbations in density and pressure. so that the total density is now the background density, which is a function of position, and the perturbation, which can be a function of anything you want. And similarly, the pressure is going to be a background pressure, the function of position only, plus P prime, which is a function of anything you want, with this assumption that rho prime is much smaller than rho naught and P prime is much smaller than P naught. And then the last assumption is that the perturbations evolve adiabatically. Okay? This is one of the common approximations. Another one would be to assume that these perturbations are isothermal, meaning that, so this would be to say that they evolve so fast, there's no time for any heat transfer in the perturbations of the fluid. The isothermal assumption would be the opposite, meaning they're kind of slow and it has time to adjust to the background temperature. So right now we're going to do the adiabatic case. But again, this is an assumption that should be checked. So let's go back to a mass conservation equation here. Now I've written it in this normal form. And I'm going to plug in rho is rho naught plus rho prime. And so the only place where that comes in is going to be here and here. And then we're going to do this trick, which is to say any perturbation that is small, I'm going to, anytime it appears in a quadratic sense, so as a product of two small perturbations, I'm going to neglect it. So for example, here, U is assumed to be small because there was no fluid motion in the background. And rho prime is small, so the product of rho prime and U is going to be quadratically smaller than the product of rho naught and U. Another way to think about it, if you want to, here I have rho naught plus rho prime, and rho prime is much smaller than rho naught, so I'm going to neglect it. And here, the background state, if you remember, was assumed to be steady, so I can remove that bit. So I'm just left with d rho prime dt plus d of rho naught U equals 0. So that's the linearized mass conservation equation. For the momentum conservation equation, so remember I've assumed there's no other forces than pressure. So you do that trick, you substitute rho is rho naught plus rho prime here, and P is P naught plus P prime here. Now, U dot grad U is quadratic in U, so it's going to be very small. So I'm going to remove it. And rho prime, I'm going to neglect it in terms of rho naught, so I'm going to remove it as well. Or you can say rho prime times du dt is quadratic in perturbation, so I'm going to remove it. And then the gradient of P naught has to be 0, otherwise the background is not a steady state. And so you're left with just gradient of P prime. So that's going to be your linearized momentum equation here. And finally, if you assume the equations, the perturbations are adiabatic. So remember, if it's adiabatic, the derivative of the entropy following the fluid is going to be 0. But this only applies to the background, to the perturbation entropy. And by using the equation of state, you can rewrite it as dp prime by dt is gamma p naught over rho naught d rho prime by dt, where this quantity here, gamma p naught over rho naught, is called the adiabatic sound speed. Now, each of these big D by dt's is a partial with partial t plus u dot grad. And the u dot grad part is going to be quadratic when you multiply it by the perturbations, or when you apply it to the perturbations. So the only thing you're left with is the actual derivative with respect to time, the partial. So this becomes partial p prime to partial t is equal to c squared partial rho prime by partial t. So the key was to say, I'm assuming a background state, I'm assuming perturbations exist that are small compared with the background, and I go through all the governing equations one by one and linearize them. And here, putting it all together, we now have these 4 equations. So these are the ones we just derived. And then it's just a little bit of algebra to try and combine them to create one equation for one variable. So there's lots of different ways of doing it. Here, I've chosen to focus on d rho prime dt. So on the one hand, from here, you can take d rho prime dt and write it as 1 over c squared dp prime dt. 1 over c squared dp prime dt. And then when I take the second derivative of rho prime, I get a second derivative here. And similarly, d rho prime dt is minus div of rho naught u, but d by dt of rho naught u is minus grad p. So when you combine these two together, you get that the second derivative of rho prime is grad square p. And so putting now this and this together, And remembering that c is independent of time, then you can take this out and then multiply on the other side, and you get d2p prime by dt squared is c squared grad square p prime. Now, you might be wondering why I did it this complicated way. Because that way also applies, as it turns out, if c squared is not time independent. So if you actually care about sound waves in media that are not time independent, you can still apply the same technique and get the same result. Okay? But up to here. And then this did assume that the sound speed was time independent. So this is more general. And if the sound speed is time independent, you recover this. Now, this one, anybody who's done a little bit of undergrad PDEs or grad PDEs should recognize this equation as being a wave equation. Okay? So now you expect waves to develop. And these are specifically these sound waves we've been hoping to get. And it immediately tells you a number of things. It tells you that this adiabatic sound speed, is indeed the correct wave speed for these sound waves. Now, up to here, everything was very simple. Going beyond that gets really complicated very quickly. So if you make some further assumptions about the background you're considering, you can get analytical solutions for these sound waves. So for example, if you assume that c squared is constant both in space and time, so before that, c squared could be dependent on space, but now we're going to assume it's independent of space as well. It's just constant everywhere. Then you can assume plane wave solutions, which are e to the ik dot x plus omega t. And so this just gives you, if you have these exponential solutions, the advantage is that any derivative becomes extremely simple. And I think Luis actually used it this morning. So if you have d2p by dt2 equals c squared grad square p. Now, the d by dt of an exponential, okay, that's just going to pick up whatever term is in front of t. So that's just I omega. So this is p, right? So I pick up an I omega. So this is just I omega p. And then if I have a gradient, that is just gradient p. Now I'm going to pick up d by dx, d by dy, d by dz. The d by dx gives me ikx, d by dy gives me iky, d by dz gives me ikz. So that's just ikp. And similarly, a divergence would be, divergence of a vector would be ik dot v. Okay? So if you combine all of this, from the second derivative with respect to time, you get a minus omega squared. And from grad squared is div of grad. So you're going to get an ik dot k. So you get a minus k dot k p and with a c squared here. Okay. So that then shows that the pressure perturbation disappears, and you're just left with the dispersion relation, which is omega squared is c squared times k dot k. And I wrote it this way, but if you prefer, you can just write it as the total amplitude of k squared. So these are these plane wave solutions. And as you know, these plane wave solutions are just oscillatory solutions. So basically sines and cosines that exist forever in space and time. And if you have such solutions, these sines and cosine, there's a unique relationship between the frequency of oscillation and the spatial wave number of the oscillation, and that is, they are related. Omega is ck. So that's a linear relationship between the two. In 1D, at least, you can also take these equations and derive traveling wave solutions from that. And the way to do it is to say that you have d2 by dt2 minus c squared d2 by dx2 applied to p. And you see that I can only do this if I'm one-dimensional. Okay? And now I can use this trick, which is to say this is d by dt minus CD by dx into d by dt plus CD by dx applied to P. And so this tells you that either d by dt plus CD by dx of P is 0, or d by dt minus CD by dx is 0. And these are two advection equations that you saw this morning. Okay? And the solutions are given here. So either you have that pressure is a function of x minus ct, or pressure is a function of x plus ct. Right? And these are these traveling waves, and I'll show you what they look like. This is an example from a Gaussian initial condition with no initial velocity. So initially you have high pressure here and zero pressure elsewhere. And what this divides into two packets that travel one to the right and one to the left, both with velocity c. Okay. Now there's a general solution that you can derive mathematically that tells you how the initial condition gets partitioned into the left traveling and the right traveling wave. And this is called D'Alembert solution if you're ever looking for it. Okay? But it only works in 1D. So the point I wanted to illustrate is for these very simple backgrounds that have constant wave speed, constant c, you have two typical behavior of the solution. One is oscillatory, and the other one is traveling. And in reality, you're going to have a combination of the two. They will both oscillate and travel together. And that's what the more complex solutions end up looking like. So in general, you're going to have what's called wave packets, which oscillate at frequencies that vary more or less slowly, with amplitudes that vary more or less slowly in the medium that's propagating. So the sound wave that I'm actually emitting towards you right now has this property that it's modulated both in amplitude and pitch. And that's exactly what you hear. Okay. Now, in general, the solutions that I gave you earlier, they're not valid. They require that the sound speed be constant in space, these two types of solution. If you think of stars or interstellar medium or wherever you want, the sound speed is never constant. Also, I had to assume, if you remember, it's really important to remember the assumptions, that the fluid was at rest with no pre-existing motion, right? Now, do you know what happens if the sound speed, the sound is propagating on a medium that is moving? You've all heard it when the ambulances in New York drive really fast. There's this Doppler effect, right? The pitch changes, the frequency changes. I'm not going to talk about this, but this is another effect, right? On the other hand, in stars, assuming they're not rotating, at the very least, the sound speed is not constant in the star. It's usually a lot hotter in the interior than it is by the surface, so the sound speed is much, much higher here than here. Now, to study that, there's two techniques, which are equally complicated or simple, depending on your perspective. One of them, and both of them are somewhat approximate in some ways. So one of them is to use this idea of localized wave packets with slowly varying amplitude and frequency, and use something called or you can call it WKB theory, you can call it ray theory. It's ultimately a multi-scale analysis, where you separate the oscillation frequency both in time and space of the wave with the modulation of the wave packet, both in time and frequency. And when you do that, you can derive equations for the envelope of this, so for how the frequency varies and how the wave number varies. And the key to everything in this ray theory is that this is still valid, but now C is this function of R. And the other key is that if the medium is time independent, the frequency is conserved along the ray paths. So that doesn't change at all. That remains the same everywhere. So if the sound speed changes, but the frequency remains the same, that tells you that your wave number must change. The wave number tells you the direction the waves are propagating. So if the wave number must change, then the waves must curve around. And that's why when you look at astroseismology talks, they always show the same plot, which shows these ray paths, which are the paths these wave packets are taking. And these ray paths are always curved, and they curve away from the region of hot, where it's hotter. Okay? So, and this, you can derive everything exactly using these theories, this WKB theory. And these kind of techniques are used very much in time-distance helioseismology or ring diagram helioseismology, okay? Not so much in astroseismology. And if you're interested, there's a, I'm happy to tell you more about this, but that would take a whole quarter to learn about this, huh, Bishek? All right, another technique for dealing with this equation when the sound speed varies is just to solve it by brute force. So you actually go back to this notion that you have this wave equation with the Laplacian of p, and you solve this numerically. Typically, if this is just a function of r and not just a function of theta and phi as well in a spherical star, you can decompose it into Legendre functions, this one, and then you just end up solving a spatial problem in the radial direction. And these are the pictures they will show you in talks on helioseismology and astroseismology. So this is the structure of the eigenfunctions of this operator, and each eigenfunction vibrates with a different frequency. But the key is that different eigenfunctions have different spatial patterns that propagate more or less deeply in the star. And by comparing the frequencies of these eigenfunctions, you can also infer something about the sound speed in the star. So without going into detail, again, this is mostly a numerical exercise to solve these. So what can be done with p-modes then is to compare the frequencies that you observe in a star or in a planet, and compare that with models, and that helps you, for example, in astroseismology, to constrain stellar properties like radius and mass, and that's been done a lot using Kepler. To measure rotation and differential rotation, that's been done a lot using gravity modes in red giant branch stars and others. To measure the size of convective regions in a star, especially core convective size. And in some cases, that's been done by some people here, to detect magnetic field inside stars. So there's a lot of amazing things that's been done using sound waves and mixed modes, mixed sound and gravity waves in astroseismology. And in the sun, which actually predates a lot the study of astroseismology, they use sound waves to measure the sound speed profile in the sun with great accuracy, to find the position of the base of the convection zone. If you've ever looked, the base of the convection zone is known with 3 digits. 0.713. Okay, so this is thanks to helioseismology. We can measure the differential rotation profile in the sun with some accuracy and detect emerging magnetic structures, active regions on the other side of the sun. They do lots and lots of cool things with sound waves. But from the perspective of this lecture, they're a good way of illustrating how general stability analyses and wave analyses work. Any questions so far? So more generally, if you're not necessarily interested in sound waves, but in other things, here is the general idea for proceeding. And that will make me happy because I'll talk a tiny bit about instability. So if you want to figure out how perturbations on a given state evolve in time, the first thing you do is you define a steady background. And again, steady is in the context of the perturbations you want to model. It just has to evolve very slowly compared to the thing you want to model. Then you assume each variable, so density, momentum, energy, etc., is a sum of a background, which is steady, plus the perturbations, and that the perturbations Q prime are very small compared to the background. You substitute into your Navier-Stokes equation the governing fluid equation, and here I've generally written them in a form that exhibits linear terms. So grad P, what else was linear? If you have buoyancy, rho G, etc. And then nonlinear term, which are your UDOG grad terms, typically. Then you plug in your Q into this operator. So the Q naught being steady, it disappears from the dq dt. The linear operator, you can just separate it out. So it's going to be LQ naught plus LQ prime, because it's linear. And then the nonlinear operator, you're going to linearize it using Taylor expansions. So you're going to say this is n of Q naught plus Q prime, but because Q prime is small, you say that this is n of Q naught plus dn dq times Q prime. And here you have to be careful. This is a Jacobian, not just a straight derivative. Okay. Now the key is that I have this L into Q naught plus the nonlinear terms at Q naught. And this has to be 0 because your background is steady. Okay, so L of Q naught plus nonlinear of Q naught has to be 0, otherwise dQ naught dt is not 0. So this and this disappears, and you're just left with L times Q prime plus J naught times Q prime. And that's a linear operator. All the nonlinearities at this order have been disappeared, actively disappeared. And so the only thing you've got left to do is to find the eigenvalues of that operator. So, because if I find the eigenvalues, so that says L plus J Q prime is lambda Q prime, I then know how this evolves in time. Okay? So this is very similar to what Louis was talking about this morning. So, and if you find pure imaginary eigenvalues, you get waves, which we did for the sound waves. If you find any eigenvalue with a positive real part, any of them, that's an instability. Okay, so that means your solutions will grow with time. So you can completely generalize everything we did for sound waves and obtain both waves and instabilities. Okay. Now, I just want to warn everybody, this fourth part, the devil's in the details, right? It can get really hairy, really complicated. And specifically, the more complex the background you're considering, the harder that thing is to do. Especially if it's multidimensional, if you have lots of physics in there, it gets really complicated really quickly. And also, the geometry and the boundary conditions you apply really matter to whatever you're finding. So if you do this problem, and you want to get any kind of analytical solutions, you have to consider simplified geometry, simplified boundary conditions, and simplified physics. But of course, the solution you get are very specific to the simplifying assumptions that you're making. And they are not always justified. So you have to be careful. You always have to find a posteriori, figure out what assumptions you made are actually fine. And the bottom line, if you read papers and somebody's claiming here there's this instability, or hey, there's these waves, you must absolutely be clear what assumptions were made in deriving this dispersion relation or that instability to figure out whether it makes sense for your own problem. Okay, because everything can be very specific. So, any questions about this? I'm going to move on to the thing I know even less about, which is shocks. All right, so in the low-density astrophysical plasmas that probably most of you are interested in, the sound waves I've been describing very rarely stay low amplitude. There was this assumption here that they were low amplitude. Usually it's not the case, either because they were initiated with high amplitude, like blast waves or other, or because they went from regions of high density to regions of lower density and they steepened into shocks. Okay? Now, I'll explain what that means in a second, but generally speaking, sound waves never stay linear in these environments. Now, shocks are the most important effect of compressibility in gas dynamics for these objects, for example. And the reason I say that is because shocks often regulate turbulence. So, for example, in accretion disks, the amount of turbulence in the accretion disk is pretty much regulated by shocks, by the turbulent dissipation, the shock-induced dissipation of the turbulence. And it's the same here. Here, I'm not sure, actually. I know very, very little about that in cosmological or galaxy formation simulations. And shocks are very beautiful. You can observe them, which makes them a good reason for studying them in astrophysics. And you can observe them due to the dissipative processes that occur within the shock, so at the edge of the shock. So typically, and this is something I'm going to completely ignore in anything I'm going to tell you in a minute. And finally, in star formation and galaxy formation, they play a really important role in the feedback. So mostly by controlling, like again, the amount of turbulence in the environment. And also the expansion shocks, the bubbles also play a good role of injecting energy into the turbulence. So for all these reasons, people in astrophysics have been interested in shocks pretty much ever since they looked up at the sky. Now, generally speaking, they're very difficult to study mathematically unless you have a conservative system. So the conservation laws that I described earlier. These conservation laws, if you remember, ignored any dissipative process, which are the things you actually see. Okay, so we're going to model shocks in a very idealized way. to explain what we see, but we're going to neglect all the processes that lead to what we see. So I'm going to go at it from a mathematician's perspective, since I'm in an applied math department, and derive the equations of shocks, starting really simply. And I'm going to take the simplest possible conservation law. So not the ones associated with the fluid equations, just the one associated with a one-dimensional conservation law for a single scalar variable. So df dt plus div of a flux in 1D is literally just df dt plus d by dx of a flux. And the key is that flux should be a function of the quantity itself only. So that's called the conservation law in 1D. Now, the way this beautifully, however nonlinear this function is, you can always solve it analytically, which is really remarkable. To see that, you just expand this using the chain rule. So I'm going to write it as df d little f times d little f dx. Okay, it's just the chain rule. And now, if you just sneakily call this u, call this quantity here u, and call it a velocity field, then this looks like df dt plus u of f df dx. I've just named it something different. I haven't done anything magic. But now you can see this is an advected derivative. Okay? Now, mathematically, this is basically called constructing the characteristic equation. But from a fluid's perspective, even though there's no fluid here, you can understand it from the tools I gave you earlier as an advected derivative along this quote-unquote fluid that happens to be propagating at this velocity here that's given by the derivative of the flux. Okay? So this quantity f is conserved following this element that is moving with this velocity u that is given by the derivative of the flux. The trajectory of that quote-unquote element, hypothetical element, is just dx dt is u, which was the derivative of the flux with respect to f. And so you can integrate that with respect to time, and you get that x is u times, or if you use that, x of t is f of f prime of f times t plus x naught. Okay? So this is telling you the trajectory of this hypothetical element, and along that trajectory, little f is constant, remember? And that's why I can do this, by the way, because otherwise there might be a time dependence in here, right? But because little f is constant along the trajectory, I can just integrate that trajectory. Now these equations, this x of t is called the characteristic of that particular conservation law. And this is trajectory. So here is basically how this then works. Here is a 3D plot, and I'm terrible at drawing in 3D, so I'm going to have to imagine it. Now this is my initial condition, f of x and 0 as a function of x. And suppose it's this black line, right? So this is the z-axis is just going to be the size of f. Now, for each initial condition, I know what f is, right? It's the height of the black line. So I can construct the flux of f and the derivative of the flux of f at that initial condition. So I know what this is at the initial condition. And then I can create the trajectory of that element. And you'll know what kind of function this is, pre-calc. This is a straight line, right? So I can draw these straight lines emanating from my initial condition. And these are these red lines. And because f is constant along the characteristic, they really are straight lines, okay? And their slope is given by 1 over the flux, 1 over the derivative of the flux. And then finally, the solution is basically there to be taken because the initial conditions are conserved along these red lines. So as we evolve them in time, time being in this direction, the function is just, the f is just conserved. So you see how high this was above this blue line? It's exactly the same height above this blue line. And you see how high it was above this blue line? It's exactly the same above this blue line. Okay, so the function f is just conserved along these red lines. So this initial condition, which had a hump of that size, because the characteristics are converging to one another, I'm just compressing the hump a little bit, but the height doesn't change because the function is conserved along the characteristics. Okay? So this is how you normally solve conservation laws. Has anyone never seen this before? Good, so you've all seen this before. Great. So now you can see there's 2 possible problems that might happen with that. Problem number 1, characteristics diverge significantly, and there ends up being regions of space where no information is propagated from the initial condition. So if all the characteristics on this side go to the right, and all the characteristics on this side go to the left, and there's this region emanating from this point into which no characteristic go, you don't know how to fill that domain with information. So that's problem number one. And I'll get to that if I have time. Problem number two, which is where we come in, is what if characteristics cross? There's no reason that they shouldn't. So this characteristic coming from this initial condition goes that way, this characteristic coming from this initial condition goes that way, and this one goes that way. And at this point, more than one are present. So at this point in time and space, there's information coming both from the left and from the right and from the middle, and you don't know which actually to take. And when this happens, you end up getting a shock, and it's a mathematical shock, okay? So the way to resolve it is to say I'm going to partition space by saying, well, solutions coming from the left are going to be true up to the shock. Solutions coming from the right are going to be true up to the shock. And I need to figure a way of deciding where is the shock going to be. But if I can find a meaningful way of creating that shock curve, I can indeed partition space into the left solution and the right solution. So the main question is not so much what is the solution, is how do you figure out what this shock curve is, okay? So to do that, you can't do it with the tools we've had so far. You have to go back to the original conservation law, and this is where the fact that it's a conservation law is really crucial. So what you do, so this is at a given time t, this is where my shock is, right? I have a solution on the left and a solution on the right. And I'm going to take an interval AB selected on either side of, where A and B are on either side of the shock. And it doesn't matter which way you pick A and B as long as one is on the left and one is on the right of the shock. Okay? I'm going to take my initial conservation law, which was written in this form, and I'm going to integrate it between A and B, so over that interval. Okay? Again, A and B are fixed in time. That's the only requirement I have of them. They're not moving. So if they're not moving, I can switch the order of the integral and the d by dt once I've integrated. The integral between A and B of this term is really easy to take because I'm integrating a derivative. So it's literally the flux at B minus the flux at A. All right, so that bit's easy. Now, and this is completely general, right? Now here's the really smart trick, is to say now I'm going to split that integral between A and B as an integral between A and the shock, and then the shock and B. So I'm splitting that. So d by dt, the integral between A and the shock, and then, sorry, there should have been a bracket around there, and the shock and B. And now it's a little bit trickier because that time derivative is going to know that there's a moving shock. And you know what to do when you have derivatives of an integral, and then there's a bit of the integral, bit of the boundary of the integral that depends on time, right? You have to be really careful because you have to take a derivative both of the interior and of the moving boundary of the integral. So that one becomes d by dt of x times f at x, all right? And because here this was all over this left interval, it's going to be the left function. And then there's the derivative, then there's the bit where you put the derivative inside the integral here. So these two terms come from this integral. And then on this side, the derivative of here is going to pick up a minus because it's the bottom part of the integral. And it's going to pick up the function on the right because this is all about stuff that's happening on the right of the shock. And again, you have this bit, which is when you move the integral, the derivative back inside the integral. So I've done nothing but now split this into two and express the conditions, the derivative of the integral where the shock is. And now there's one little extra bit, which is now I'm going to plug back in my conservation law into the FDT. and say that this is minus d by dx of f of f. And some bits are going to cancel this one. Oh, sorry, some bits of here are going to cancel this one. Some bits of here are going to cancel this one. And you're going to left with the flux at the shock front. And so this is what you're left with, right? So I've factored in the the excess dt, and I'm left with the flux function on the left minus the, oh, that should have been a right, apologies. Flux function applied to the function on the left minus flux function applied to the function on the right. And so this is what are called the Rankine-Hugoniot jump condition. Rankine? I don't actually know. I might be mispronouncing this. So the dx dt, you can write it as the jump in the flux across the shock, because that's exactly what it is. Jump in the flux across the shock minus the jump in the function across the shock, and often written as these square brackets. So this actually means the jump in the flux across the shock. So f on the right minus f on the left. And this is the jump in the function across the shock, a little f on the right minus little f on the left. So this is really saying that the velocity of the shock is controlled by the ratio of the jump in the flux to the jump in the quantity. So if you want to do an example, you take Berger's equation here. So du dt plus u du dx, and you write it in the conservative form. So that's du dt plus d by dx of u squared over 2. So that's your flux. I'm going to take initial conditions that already have a shock just for simplicity. So the solution on the left is 1 everywhere. The solution on the right is 0 everywhere. And it's almost irrelevant what the characteristics are. You just know that there are such characteristics. They happen to cross, which is why I care about this problem. But everything that's followed on these characteristics here, u is going to be 1. And everything that comes from this characteristic here, u is going to be 0. All right? So in addition, the flux of u, which is just u squared over 2, all the fluxes on the left are going to be 1/2, and all the fluxes on the right are going to be 0. Right? So that makes it really easy to solve for the shock curve, because you just get that the velocity of the shock, flux on the right minus flux on the left, 0 minus 1 times 1/2, and quantity on the right minus quantity on the left, so 2 times 0 minus 1, and all of this is 1/2. So that tells you the velocity of the shock for this particular problem. And so the shock curve, you integrate that in the function of time, you get that the position of the shocks is t over 2 plus wherever it was initially. Okay? So in order to find how fast shocks propagate, you don't even need to know anything about characteristics. You just happen to need to know that they cross, and you need to know what are the initial conditions that are propagating on each of these characteristics. So that makes it really easy to solve. Now, there's usually a huge disconnect between this and then what people learn in physics of astrophysics time courses, which are these jump conditions for shocks. And for the longest time, I didn't know how you went from A to B, so I had to work that out for this lecture. So going from this, which are very simple shocks in 1D for scalar quantities, how do you do shocks for this? Okay, so these are the fluid equations written in conservative form. And what I want to do is now to write it as a vector. And I'm going to do this in 1D for simplicity, though it can be generalized to multiple dimensions. So the vector is going to be rho u, and energy. And I can write this as d by dx of whatever the fluxes are. So rho u squared plus p, and eu plus pu. Okay, so that's my fluxes. So this time it's no longer a scalar conservation law, it's a vector conservation law. Right, so I have 3 quantities that are being advected and conserved. So finding the correct, more generally, you can then do that for any size. You can write any conservation law in vector form. If you have multiple quantities conserved, you just have a vector of quantities conserved and a vector of fluxes, and it becomes that. Right. So now you can generalize that for any dimension. And as it turns out, it's not too complicated to do. So this was actually done kind of by Louis this morning. So if you take your conservation law and you apply the chain rule, as we did earlier in 1D, instead of getting a normal derivative, you get a Jacobian here. So for each function I, you write dfi dt is dfi dfj dfj dx summing over j. And so that becomes your Jacobian of the fluxes with respect to Fs. So to obtain the characteristics, which you don't often need, actually, only if you really need them, if J is diagonalizable, and that's the tricky part, then you can write it as left eigenvectors times diagonal matrix times right eigenvectors. You multiply on the left, you multiply on the right, and then you end up with distinct characteristic equations, one per quantities that you're conserving. Okay? And I believe that maybe Evan is going to do this later for a specific problem, or if not, you can find this in any textbook that does that. The reason I don't want to focus too much on it is I've been charged with making sure you all know your jump conditions. So, and it's actually a lot easier to do too. So you go back to this equation and you play the same trick of integrating across an interval AB. And so you end up with exactly the same thing. You play that trick of inserting the shock and then integrating between A and the shock and then with the shock and B. And you end up with the derivative of the position of the shock with respect to time times the jump in the quantity F is equal to the jump of the flux for each component of that equation in turn. So if you then put it for the fluid equation, in a sense, or just to be specific, there's nothing in what we did here that said that that can't be a vector. Everything carries through. You can do it for a vector. So this is what we do here. So you do it for a vector. And so it tells you that these are the shock equations in a frame at rest. So the derivative of the shock with respect to time times the change in rho is the change in the momentum. This times the change of momentum is the change of rho u squared plus p. And this times the change in energy is change of E plus P U. And you don't often see them written like this. You often see them written in the rest frame that's moving with the shock. In the rest frame that's moving with the shock, you have to say u minus u shock. So it becomes a u prime. And then all the right-hand sides disappear. Sorry, left-hand side disappear. And you're just left with that. So these equations, which says the jump in momentum across the shock is 0, jump in rho u squared plus p across the shock is 0, and jump in E plus P u across the shock is 0. These are expressed in the rest frame, moving with the shock. And of course, never forget there's an equation of state. That's also going to relate quantities on each side. Okay? So finally, how do you use this? Well, let's count how many equations we've got. We've got 1, 2, 3, and then 1 on each side. So that's 5 equations. 4, yeah?
If you allow to have more than one state in the downstream, can say as in the case of intermediate shock, can you represent that using two different capital Fs?
You're already beyond my knowledge of shocks, so I think somebody else will have to take that question.
So this just assumes that you have one state in the downstream. So can you have
One state as in one P rho U, yeah.
if you have given P2 rho and rho 2 and you have two different states, does it mean you will have to represent it with F1 and F2? Can you do that?
Well, you can have multiple shocks. I mean, what I didn't say here is once you have several characteristics traveling at different speeds, you end up with intermediate shocks. And so you have several intermediate states. Is that what you mean? And each intermediate state would have its own jump conditions. But I don't know if that's actually what you actually asked. Okay, sorry. Like I said, I really don't work on this. So you have a total of 5 equations for 8 quantities, which are density on the right, density on the left, pressure on the right, pressure on the left, velocity on the right, velocity on the left, and then internal energy, say, on the right, internal energy on the left. So that's 8 of them. So of course, it's not a problem that has a unique solution. And so either you must know something about the state of the system on one side of the shock, and you then infer what's on the other side. So say, if you know 3 of the variables on one side of the shock, you can infer what's happening on the other. Or often it's written as you can obtain from these 5 equations for 8 variables, you end up with quantities relating the jump or the ratio of the quantities on the left on the right instead, right? So there's different ways of using that information depending on what you want to do. And so the funny thing is that despite all of the caveats I say, well, we don't know anything about what's happening actually in the dissipation regime within the shock, you can still learn a lot about shocks from these conservation laws because they are correct everywhere except within the shock. Okay. Let's just talk for a second about expansion shocks. So these are the ones where no characteristic go. So what do you do? One of the very important things is not to create any information out of nothing. It's called the entropy condition. So any information that enters that region can only come from this one point. That's the only thing you're allowed to do. So basically, the solution is to create characteristics that all emanate from this one point. And that ends up being called an expansion fan or an expansion shock. And the trick is to fill them with characteristics. Now, and assume that on each characteristic, or the equation for each of these characteristics is still given by this quantity, which is what we derived in the general case for outside of the expansion shock. And then to do this little mathematical trick is just to solve for f. So I'm going to solve for whatever we want, assuming this is the form of the characteristics. And you get that f is x minus x naught over t. And you apply the inverse of f prime to that. So inside that expansion shock, the solution is the inverse of f prime, so which was the derivative of the flux with respect to f, applied to x minus x naught over t. So that's the solution you get. And it's the only solution that you can create that actually is satisfying this entropy condition or a causality condition if you want. Okay? Yeah, that wouldn't happen if you didn't have an yeah. So this was all kind of mathematical. From a computational perspective, which is what Evan will talk about later, it's really important to model shocks properly. Now, I mentioned that shocks are ubiquitous in most of these environments. And so if you have a code that does not handle shocks, it's completely hopeless. So all of the work that's done in star formation, galaxy formation, for instance, typically uses codes that are shock resolving or shock capturing. I'm sorry, not shock resolving, shock capturing, meaning that they handle shocks well. And the only really good way to do it is using finite volume algorithms, which are based on the conservation laws that you're trying to model. And so I believe that in that talk, you'll see a lot of diagrams like that, which capture what happens to a shock that propagates between grid boundaries of two cells that you're trying to model. So this is a Riemann problem here. And I'm not going to say more, because I believe you'll hear more of that later. But all of the tools that I derived today, the jump conditions, the expansion shocks, you'll see they're actually going to be used to do that. And I want to finish by saying, suppose you're armed with your fluid equations, and suppose you're armed with your shock capturing scheme, and with a lot of faith in your code. Even if you have that, it's still impossible to model any of these problems. Maybe that's a slightly pessimistic view. But basically, the problem is in any of these systems, there's an enormous range of scales to model. Let me just take an example. In the sun, the viscous dissipation scale, associated the Kolmogorov scale, if you know what it is about a centimeter. The sun is 10 to the 11, 10 to the 10, 10 to the 10 centimeters. It's enormous. So you would have to have a code that can resolve more than 10 orders of magnitude. And the problem is just exacerbated as you go to larger and larger scales. Okay? So even armed with the best code in the world, you will not be able to resolve the small scales. So, and the problem is that large and small scales influence each other. So large scales set the conditions under which the small scales develop, and the small scales regulate the development of the large scales through feedback. And here I say turbulent feedback, but it could be any kind of feedback. Let's just take some example, right? In accretion disks, you have the large scale, which is your global differential rotation, your scale height of the disk, and these provide the conditions under which things like turbulence, dust processes might take place. But the turbulence itself is what regulates the angular momentum flux that controls the disk evolution. In star formation, the large scale might be your collapsing cloud that provide the stars, and it's the winds from the stars that create the turbulence that's going to regulate star formation. So at any point, any problem you can think of, you'll have this two-way feedback between large scale and small scales. And it's really almost impossible to know how to deal with that. And this is basically what you folks in the school are going to work on, I understand, this problem of multi-scale. And it really is the number one problem in astrophysics, how to deal with this range of scale. So even if you understand everything, there will still be that to solve. So on that, I'll finish. Thank you very much.